All right, today we're going to be covering the control aspect of product design. That is, using electronics to be able to control individual circuits. So we're going to go through all of the different concepts that you have to know for that. First thing is you need to be able to draw a block diagram for an open loop system. This is actually really simple. An open loop system, you have an input, a controlled system or a control circuit, and then an output. That's all there is to it. Okay, this is something like if you have a dimmer switch on your overhead lighting. Okay, you turn the light level up to whatever you want it to be. You have the input, which is the dial. You have the control circuit, which is the voltage and the current running through the light, and then you have the output, which is the amount of light that comes out. That's all there is to it. Now, this is limited in that you don't have any way of knowing exactly how much light would be coming out of that overhead light. In positioning systems that are used in robotics, this is known as dead reckoning. An example of this would be if you were to have a robot, for example, and you tell it to go forward in a straight line for 1 second. While that sounds great, there are many variables that can affect that. One of the motors can be underperforming. So if you have a skid steer system, what would happen is the drive system would take it in a curve. It wouldn't go in a straight line because one motor is going slower than the other motor. Or there could be obstacles in the way, so it could run into something and just sit there and drive against it for a full second and wouldn't actually travel in a straight line for 1 second. Or there could be something on the surface, on the driving surface, that causes one or both wheels to slip. All of these you will create errors, and with a purely open loop system, with purely open loop control system, the errors tend to be cumulative. That is, if it's driving slightly off to the right, let's say you have several commands for a dead reckoning skid steer system. Drive forward for 1 second, turn to the right for 1 second, drive forward for 1 second. What'll happen there is if one of those wheels isn't going exactly the same speed as the other wheel, it'll drift, and then the turning will make it even worse, and then going farther will make it even worse. So the more that it drives with no feedback loop, the lower the accuracy of the actual completed system is. Consider it like a stovetop. Okay, if you've ever cooked on a stovetop, the burners have settings: low, medium, high, whatever. Okay. There's no sensor that feeds back to the stove to tell it if it's actually at that temperature. There's nothing that says, all right, I want you to take this skillet exactly up to 300 degrees. Okay? It's up to whoever's cooking the food to sit there and monitor and make sure the food's not getting burned or getting undercooked. Now compare that to a closed loop system. A closed loop system, you have the input, the control system, and then the output, but then there is what's called a controller, a feedback loop. Now the feedback loop often takes the form of some form of electronic sensor. Okay, if we're going back to the robotics example, it would be like an encoder on one of the wheels. An encoder is something that measures rotational speed. You have the encoders attached to the wheels. That way, if they're driving and one motor is underperforming, like I gave you in the example, the feedback loop from the encoder will tell the main computer, okay, this motor isn't spinning as fast as the other motor, so it'll slow down the other motor to match speeds, or it can slow down the other motor to match speeds, so that way it'll drive in a straight line. So you have that effect. Or you can have other outward-facing sensors like ultrasonic rangefinders, line detectors, camera tracking, all sorts of possibilities that are on there. Now that control will then feed back in the main control system will adjust the input so that you get the output that you want. Now the the sensor feedback, the important thing to realize about it is that it reduces your error. Okay, the more sensors you have, or not necessarily more, but the more accurate sensors you have feeding back into the control system, the more accurate your output is going to be. So, for example, in a closed loop system, that's more like, not like a stovetop, but rather the oven. Inside the oven, when you set the you set the temperature for an oven. Okay, you don't just say low, medium, high like you do on the stovetop. You say we're going to cook this at 350 degrees. So you turn the dial on the oven to 350 degrees. It heats up the internal enclosure, and when it gets to 350 degrees, it stops applying heat. There's a sensor in there that says, okay, we're at temp, turn off the heat, and it relies on the insulation and the mass of the actual unit to retain the heat. If the temperature dips below a certain threshold, it'll turn the heating element back on and bring the temperature back up to 350 degrees. Okay, that's a closed loop system. Now, closed loop systems overcome the main advantages of open loop systems in that since there's a feedback or a control loop, that input is dynamically controlled. If you don't have that, if, for example, you were cooking and you set your stovetop too high, it's up to the person who's cooking to lower that temperature so it doesn't burn the food. Okay, with the closed loop system, that's automatically monitored and it maintains the exact temperature that you need. Most systems use negative feedback rather than positive feedback. For example, the example that IB provides is negative feedback systems will stabilize systems. For example, a lathe spinning at a particular speed will slow down when put under load. The sensor detects the slowing down and the feedback will reestablish the required speed of the lathe. That is, negative feedback is simply if it's not doing what it should be doing. So in the example of the oven again, if the temperature is not at 350 degrees, that's a negative feedback. It doesn't say, okay, it doesn't have a positive feedback. It just relies on when it's not doing what it should be doing. Like the encoder on the control system. If the motor is not spinning at the right speed, it then will apply more current or slow down other motors to match its speed. An encoder, this is basically what an optical encoder looks like, this diagram. You have a light source. This is one type of an optical encoder. There's actually many of these. There's a disc that has holes or markings on it, and then there's a light source and a photodetector. And the light source provides a source of light, and then the photodetector receives it. If it's got holes in it, like a simple disc like this, then every time the wheel is rotating, then a pulse of light goes through and hits the optical encoder, and those pulses can be counted and calculated. Now we have optical encoders that we've used that there are they're accurate down to 1/10 of a degree. That means there are 3,600 individual little markings that can be picked up by the optical encoder on a disc that is about 1/2 inch in diameter. So they're extremely precise instruments. And they can be extremely precise. Sometimes positive feedback is used when you need to have very quick switching back and forth to maintain something. For example, to control a motor to limit a range of motion, you use a limit switch. In the example of that, let's go back to Fiddler on the Roof. The scene where they had a ghost, am I not mistaken, floating around. Now, in order to do that, they had that system that raised and lowered. Now, that was wired with a inline limit switch. Now, the way that works is when it gets to the maximum travel of the distance, the carriage physically hit a switch. And what that did was that prevented it from going any further in that direction. Okay? And in the other direction, the carriage hit another switch so it wouldn't go any further in the opposite direction. So that is a feedback loop to prevent it from overextending and falling apart. Because if that had not done, the screw would have pushed the acme rod, or the screw would have pushed the linear actuator right out and the whole thing would have fallen apart. Okay? Now, We've done a few experiments with the Arduino already, but let me explain to you exactly what an Arduino is. It is an open source. That means it's free to build and modify. When they came out with this design, I'm not sure when they came out with the original Arduino. It was over 10 years ago, though. When they came out with it, they made the decision to make the design open source. Not just the software, but the hardware. They provided the schematics online, and that anyone is free to basically buy the individual microcontrollers, timers, resistors, capacitors, and build their own Arduino, and then sell it if they want to. It's completely open source, and so there's a lot of clones that are out there. Sometimes you hear them referred to as PICs, or programmable interface controllers. Don't know if that's exactly the most accurate term, because everywhere I've seen and everything that I've seen about the documentation, it calls it a microcontroller. And the actual devices that are on there, in this example, AT Tiny 45s are used on the Arduino Unos. Those are listed as microcontrollers. Now, PIC originally, the term PIC, P-I-C, originally stood for peripheral interface controller, because it was used on it was used to control peripheral components for larger computer systems. It was basically these were used to control like printers on very old computers, or optical output screens, or anything else. They weren't part of the main computer, so they were peripheral interface controllers. Gradually, the name and the purpose changed, and they changed the name to programmable interface controllers. Now, like I said, the Arduino, we're going to cover these in more detail in a little bit more, but they're extremely useful in control systems, because a lot of control systems use digital circuits like you've seen so far. Right now we've only blinked some LEDs, but you can put sensors on these. So, any questions?